Welcome to Lecture 24, in which we begin to talk about one of the most important topics in the course, which is sequential circuits. And we'll begin this discussion by looking at an example. The example is shown here. The output of the circuit is labeled Z, and that is the output of this exclusive OR gate shown here. We have two flip-flops in this problem, and as you can see, both of these are D flip-flops. For this flip-flop on the left, we've labeled the output as A and A prime, and for the one on the right, B and B prime. And since both of these are D flip-flops, we'll go ahead and, in order to help us distinguish between the D input of the A flip-flop and the D input of the B flip-flop, we'll label the D input of the A flip-flop as D sub A, and the D input of the B flip-flop is D sub B. And you see that D sub A and D sub B are both functions of the outputs of the flip-flops and the input to the circuit, which is X. And so our goal is to understand how this sequential circuit works. And for the sake of this discussion, we will assume that both of these flip-flops are positive edge triggered flip-flops. So how do we go about trying to understand how this works? Well, the first thing that I would suggest that you do is, for this exclusive OR gate down here and for this OR gate, you trace back and make sure you understand what the inputs are. So this is A that's coming in here to this OR gate, so I would recommend that you go ahead and label that as A right there. And similarly, this second input to this exclusive OR gate here is B prime, and so I would label that accordingly down here. Now, once we've done that, we can easily identify what D sub A and D sub B are, and that is what I would recommend to you as the first step in trying to understand a sequential circuit is, and I'll go ahead and label this as 1, excitation and output equations. And what I mean there is we want to find equations for D sub A, which is one of the excitations, D sub B, which is the other excitation, and Z, which is the output. And this is very simple. If you look at the diagram, we see that D sub A is X exclusive ORed with B prime. And let's remember what that means. That means X ANDed with the complement of B prime, which of course in this case will be just B, and that gets ORed with X prime ANDed with B prime. So that's one of our excitation equations. D sub A is equal to XB or X prime B prime. And D sub B, well, D sub B is just the OR of A and X. So we have A ORed with X. And these two equations here constitute the excitation equations for this problem. Now we can also, scrolling back up, we can also get the output equation, and we see that Z is the exclusive OR of A and B. So we can write that down. Z equals A exclusive ORed with B, which is A, B prime, or A prime, B. And that is the output equation. Now, there are a couple of other comments I'd like to make. First of all, in this sequential circuit, we only have one output, Z, but it is possible for a sequential circuit to have a number of outputs, Z1, Z2, Z3, and so there could be just one output equation, or there could be multiple output equations, but there should be one output equation for each output that you have in the circuit. That's one comment. Another comment is to note that Z, our output in this case, depends only on the states of the flip-flops. It depends on A prime, B, and B prime, but it does not explicitly depend on the input X. And so when that is the case, let me draw an arrow up here. This is called a Moore circuit because the present output is not a function of the present input. Now, after we get through with this circuit will probably occupy us for this entire lecture, but in the next lecture we'll look at what's called a Mealy circuit, and in the Mealy circuit the present output does depend on the present input. But in this case, the Moore circuit, it does not. So here are our excitation equations and the output equation. Now the next step I'll do is something that is not in your book, but I think it is useful, and that is to have what's called an excitation table. And the excitation table will look like this. On the left-hand side of the table, you'll have your states, A and B. And then in the next two columns, or the next columns, will have information about the excitations. So we'll do it this way. We'll say D sub A and D sub B. But what the value of the excitation is equal to, D sub A and D sub B, we can readily see from our equations up here, the excitation equations, that will depend on X. So I'll put down here just below that, I'll say X equals 0, X equals 1, and here again X equals 0 and X equals 1. And then frequently, and even though it's called an excitation table, we'll go ahead and include information about the output as well. Now in a Mealy machine, we would need to have different columns for the output when X is equal to 0 and when X is equal to 1, because remember, the output Z would depend on X in a Mealy machine. But in a Moore machine, the present value of the output Z does not depend on X, not on the present value of X, and therefore just one column will suffice for Z. So this will be the outline of our table, and of course the 4 possible combinations of our states are given right there. And so this is a way that we could draw the excitation table. So now what we want to do is use our excitation equations and the output equation to fill in all of this data. let's go ahead. Let's start with maybe the easiest one, which is the output equation. And so the output equation, remember, z is equal to a b prime ORed with a prime b. So when both of these are, when a and b are both equal to 0, this will be 0. But when a and b are different from each other, we know that's when the exclusive OR will be equal to 1. In other words, when a is 0 and b is 1, that will force the second term here in our expression for z to be 1. And likewise, when a is 1 and b is 0, that will force the first term here to be 1. So that's the way the exclusive OR function works, is that if you exclusive OR a and b, then when a and b are the same, the result of the exclusive OR is 0, but when a and b are different, the result of the exclusive OR is 1. And you can see when both of these are 1, this would be 0, and this would be 0, so the whole thing is 0. Okay, so that takes care of z, and now we need to find the values of d sub a and d sub b in each of these cases. Okay, so let's go ahead and fill in this column first for the x equals 0 column for d sub a. Okay, so for d sub a, you can look at it like this. When x is equal to 0, this first term will disappear entirely because 0 ended with anything is 0. And then also in this case, when x is 0, x prime will be 1. So really, d sub a is just equal to b prime when x is equal to 0. So that means that we have 1, 0, 1, 0 in this first column for d sub a. Now, let's go over that again to make sure everybody followed it. The expression for d sub a is d sub a equals x ended with b or x prime ended with b prime. Now, we're trying to fill in right now just the x equals 0 column. So when x is equal to 0, this first term drops out, and here in the second term, since x is equal to 0, x prime is 1, and 1 ended with b prime is simply b prime. So in this first column, we will simply have the values of b prime, and so here's the values for b, and so we just complement that in each case. 0 complemented is 1, 1 complemented is 0, 0 complemented is 1, 1 complemented is 0. And that's how we do that one. Okay, now let's look at the second case, when x is equal to 1. Well, when x is equal to 1, the prime of 1, or the complement of 1, is equal to 0, and 0 ended with anything is 0. So when x is equal to 1, the second term disappears. What about the first term? Well, x is equal to 1, and 1 ended with b is b. So when x is equal to 1, d sub a is simply equal to b. And so we come down here, and we see that's easy. 0, 1, 0, 1. That's just setting d sub a equal to b whenever x is equal to 1. Okay? So I hope that you followed that. And now I would suggest, in order to test your understanding, that you stop the video for a moment and try to fill in the two columns for d sub b, and then come back to the video. Okay, so let's see how this will go. If we want to fill in for d sub b, again, we do it one column at a time. In the first column, when x is equal to 0, we get d sub b equals a ORed with 0, which is just a. So in this column, d sub b is always equal to a. So we look over here in a column, and we get 0, 0, 1, 1. And now in the x equals 1 column, well, when x is equal to 1, d sub b is a ORed with 1. But anything ORed with 1 gives 1. So d sub b is always equal to 1 in that column. And that completes our excitation table. Now the next step is a transition table. And what the transition table will tell us is what the next state will be. In other words, how the sequential circuit will make a transition from one state to the next state. And so the labels that we'll have in this case are A and B, and then we'll have A plus and B plus, in other words, the next values. And so we'll do this like this, A plus, B plus, but that's going to depend on the value of x. So I'll say x equals 0 and x equals 1. And then, of course, as usual, we'll have z, which does not depend on the present value of x. So when we put all this together, we'll have a table, the outline of which will look like this. And we can go ahead and fill in the first two columns. And now we're ready to find the next value of A and the next value of B for each of these possibilities. Now in this case, this is a particularly easy thing to do. In some of our future cases, this will be the trickiest step in this whole procedure, is figuring out the transition table. But in this case, it's very easy. Why is it very easy in this case? Because both of our flip-flops are D flip-flops. And remember that in a D flip-flop, the next value of the output is simply the present value of D. So, in other words, our reasoning is as follows. We want to know the next value of A and the next value of B when x is equal to 0 and when the present values of A and B are as given here. Well, for A is equal to 0 and B is equal to 0, that tells us that we look up here in the excitation table, in the first row of the excitation table, and we want to know what's happening when x is equal to 0. Well, when x is equal to 0, D sub A, which is, remember, that is the input to the D flip-flop for A, that will be equal to 1. And regardless of what the present value of the output is, I mean, A happens to be 0, but that doesn't really matter, because when we know that for a D flip-flop, when D is equal to 1, then the next value of the output will be 1. So we have 1 for the next value of A. And what would the next value of B be? Well, when x is equal to 0 and A and B are both 0, D sub B is 0, and therefore the next value of B will be 0. Let's do that one more time and make sure everybody gets it. So what we're trying to do is to figure out the next value of A and the next value of B when x is equal to 0 and when the present value of A is 0 and the present value of B is 0. Now we do this one at a time. We look first at the next value of A and then we look at the next value of B. So let's tackle first the next value of A. Okay, present value of A is, as we see here, is 0. That's the present value of A. And remember up here that A is referring here to this D flip-flop. So when the present value of A is 0 and x is equal to 0, that will make the D sub A, which is the input to the A flip-flop, it'll be 1. And when the input to a D flip-flop is 1, it doesn't matter what the present state is, the next state will be 1. So that's why the next value of A plus, is equal to 1. And similarly, now if we want to know the next value of B, okay, present value of B is 0 right here. And this is for x equals 0. So we look here, here's B equals 0, and here's x equals 0. So D sub B will be 0. So the input to the D flip-flop will be 0, and therefore the next state will also be 0. So we have 1, 0 for the next value of A and next value of B if the present value of A and B are both 0 and our input x is equal to 0. Now I hope that explanation alone will allow you to fill in the rest, actually the entire remaining information for this entire table. So I really strongly encourage you to stop for a moment and try this on your own, and then come back to the video when you're done. Okay, so hopefully you had luck with that, but let's go ahead and fill it in. Again, since this is a D flip-flop, everything is just very simple. If we want to know the next value of A, we just look at D sub A, and so we're going to have, next value of A in the x equals 0 column will be this. So we have 1, 0, 1, 0. That's the next value of A when x is equal to 1. X is equal to 0. And when x is equal to 1, the next value of A will be 0, 1, 0, 1. So 0, 1, 0, 1. And on the other hand, if we want to know the next value of B, all we have to look at is D sub B. So when x is equal to 0, that gives us 0, 0, 1, 1. We already have the first 0, so we put 0, 1, 1. And when x is equal to 1, the next value, or D sub B is always equal to 1, and therefore the next value of B will always be equal to 1. So we have 1, 1, 1, 1. And our column for Z is just the same as before, so 0, 1, 1, 0. And that completes the transition table. And that is the most difficult part of this procedure, in my opinion. Don't worry if it seems a little confusing, because we'll look at plenty of examples, but do look at that carefully and try to make sure you understand it. Okay, so after you get the transition table, the next thing you want to do is to find the state table. The state table really has exactly the same information as the transition table, but we just write it in a more convenient format. What I mean is the following. Let's go ahead and we can have the same headings for our table. So we have A, B, A plus, B plus, Z, X equals 0. Sorry, I don't want to put A. Let's change this just a little bit. Instead of saying A and B and A plus B plus, let's say present state and next state. And you'll see the reason in just a moment. But other than that change, the headings, the basic format of the table looks the same. Now, to fill this table in, what makes this table a little more convenient to view, even though it has the same information as the transition table, is that we assign names to the different states. So the conventional way of doing this is to call this initial state, the 0, 0 state, is S0. The next one is S1. The next one S2, S3, and so on. And so 0, 0 is S0, 0, 1 is S1, 1, 0 is S2, and 1, 1 is S3. And now we use the same designation to represent the next state. So for instance here, we have 1, 0, and that comes down here, that's S2. 0, 1 is S1. 0, 0 here is S0. 1, 1 is S3, and I'm sure you can fill in the rest of this. We'll have S3, S1, S1, S3, and the output is the same, 0, 1, 1, 0. And that gives us the state table for this sequential circuit. And now our final step will be to produce what's called the state graph. The state graph is just a graphical representation of the information in the state table. And different people will draw this in different ways, but I'll show you one of these. So let's use circles to designate the different states. Now altogether we have 4 states, S0, S1, S2, and S3. So I'll represent these as 4 circles arranged like this. But if you wanted to have them as 4 circles in a straight line, or 4 circles you might think of this as 4 circles at the corners of a diamond, but you could also have 4 circles at the corners of a square, corners of a rectangle. As I say, you could have 4 circles along a straight line. Any of that would be fine. Just whatever helps you to understand most easily the way that this circuit works. So we'll label this as S0, S1, S2, and S3. And for a Moore machine, the output depends only on the state, and therefore we can put the output in the same circle that contains the information about the state. Notice what I mean here as we look at this table, at our state table. When the state is S0, the output is always 0. When the state is S1, the output is always 1. When the state is S2, the output is always 1. And when the state is S3, the output is always 0. So we can just put that information in these circles, 0, 1, 1, and 0. Now in a Mealy machine, you'll see that when it comes to the step where we write the state graph, then we have to handle the output a little differently, because then the output will depend not just on the state, but it will also depend on the present value of the input, and so we'll have to account for that. Therefore, the state graph for a Mealy circuit will have a slightly different look to it, but right now we're doing the state graph for a Moore circuit. So now to finish our state graph, what we have to do is use arrows to indicate the transitions that will occur from one state to another depending on the various inputs that we might have. So if we look up here at our state table, it tells us that if we are initially in state S0 and x is equal to 0, we'll go to state S2. And so we can represent that by an arrow pointing from S0 to S2, and then we'll put a 0 beside that to denote that If we're initially in state S0 and we get an input of 0, then we go to S2. Okay, what will happen if we're in S0 and the input is 1 rather than 0? Well, our table tells us that if we're in S0 and x is equal to 1, then the next state will be S1. So we represent that in this way, an arrow from S0 to S1, and we put a 1 beside it. By the way, before I go any further, this circuit is the same as one that's in the book on page 398. However, you will, if you look very closely at that, you will see that that the author chose to label the states differently. He had S0 represent the 0,0 state, S1 represent the 0,1 state, but he called the 1,1 state S2 and the 1,0 state S3, and therefore his tables will look a little bit different, but it's important to understand however he labels the states, still in the end the circuit will work the same way. In the final analysis, if we give a sample input to this circuit and we have the same initial state, then it will give the same output, and that's what's important. Okay, so resuming now, so we have two lines. This is important to check. We have two arrows exiting the S0 state, and those represent what will happen if x is equal to 0 and x is equal to 1. Now, in each case, for each one of these states, we should have two arrows exiting, and that's something to check when you finish. So let's proceed. If we're in S1 and x is equal to 0, we go back to S0. So we can represent that in this way. If we're in S1 and the input is 0, we go back to S0. On the other hand, if we're in S1 and the input is 1, we go to S3. So we could represent that in this way. If we're in S1 and we get an input of 1, we go to S3. Now what about if we're in S2? If we're in S2 and have an input of 0, we go to S3. On the other hand, if we're in S2 and get an input of 1, we go to S1. Finally, if we're in S3 and we get an input of 0, we go to S1. And if we're in S3 and we get an input of x equals 1, we stay in S3. So we can represent that in this way, an arrow coming back onto the same state. And that's in the case when x is equal to 1. And that's it. That one picture right there will give us the entire behavior of this sequential circuit. Now, the final thing I'd like to do is to point out to you, let's check this, check that each state has two arrows coming out of it. So 2 are coming out of S0, 1, 2 are coming out of S1, here's 2 coming out of S2, and 1 and 2 coming out of S3. So that looks good. Now, we don't know how many arrows will be coming into a state. We can only say that it should have, if there's one input to the system, then there should be 2 arrows going out of every state. If there's 2 inputs to the system, then there should be 4 to cover all 4 possible combinations of the 2 inputs, and so on. So there's our state graph. But one other thing I'd like to do is to show you how this might be used. So as an example, let's say that we have the following. Let's say that we're told that the initial state of the system is the 0, 0 state, and that we have an input sequence to the system given by this 1, 1, 0, 1, 0, 0, 1, 0, 1. And we want to know what the output sequence will be. What will be Z if, again, if our system, if our circuit is initially in that 0, 0 state, which remember, that's what we called S0. If it's in that state, and we have an input sequence 1, 1, 0, 1, 0, 0, 1, 0, 1, what will be the outputs? And I hope that you see that this is a fairly easy question to answer. Okay, it'll be answered in the following way. Okay, first of all, A is equal to 0 and B is equal to 0 is the S0 state. And if we look up at our picture here, in the S0 state, the output is always 0. So our first output will be 0. Now, if we're in that S0 state and X is equal to 1, where do we go? Well, here's the S0 state. If the input is 1, we go down here, but if the input is 0, we go down here, but if the input is 1, we go over here to S1. And remember, S1 is 0, 1. And in the S1 state, the output is always 1. So the next value of Z would be 1. Now, we're in S1, and the next input we get is 1. So if we're in S1 and we get an input of 1, we go to S3, which is 1, 1. And in S3, the output is always 0. So we fill in 0 for Z. And now where do we go next? Well, we're in S3 and we have an input of 0. And this tells us that when we're in S3 and the input is 0, we go to S1. So that's 0, 1. And in S1, the output is always 1. Now, if we're in S1 and we have an input of 1, then go back up here again. S1 and an input of 1 takes us back to S3. So that's 1, 1. And in S3, the output is always 0. So we put a 0 down there. And now we're in, let's go to the next one. We're in S3, 1, 1. We're in S3. We have an input of 0. So we go back to S1, which is 0, 1. In S1, the output is always 1. And so that takes care of that. Now, what about the next one? Okay, we're in state 1, and we get an input of 0. And so when we're in state 1 and we get an input of 0, we go to state 0, which is 0, 0. And in the in that state 0, the output is always 0. Now, if we're in state 0 and we get an input of 1, where do we go? We go to state 1, so that's 0, 1. And in state 1, the output is always 1, so we'll put a 1 down here. And then we see where we go next. Okay, we're in state 1, and we have an input of 0, so that takes us back to S0, which is 0, 0. And in that state, we in the S0 state, we always output 0. And now we can do one more column. If we're in the 0, 0 state and we have an input of 1, then we go to S1, which is 0, 1. And in that state, the output is always 1, so we can put a 1 down here. But we don't have any input now, so we don't know where the circuit will go next. And that concludes that's all that we can do. So if the circuit were initially in this 0, 0 state, and we input this input sequence, then our output sequence would be that. And that's an example of how the state graph can be used to predict the behavior of our sequential circuit. But remember, the state graph just represents what's in the state table, which just represents what's in the transition table. And so all of that part is really very easy, but the transition table, again, is the difficult part, because to get that, you need to look very carefully at this excitation table and understand what's going to happen in the various situations. And that will get more difficult in later examples where we have perhaps a T flip-flop or a JK flip-flop rather than D flip-flops. But there is our first example of a sequential circuit. So now let's look at some questions on this lecture. All of the questions that we'll have refer to the table shown here. This is the transition table, and we're dealing with exactly the same circuit that we had here, exactly the same, with the only difference being that now, instead of these being positive edge triggered D flip-flops, we will have these as positive edge triggered T flip-flops. And so this will be T sub A and T sub B rather than D sub A and D sub B. But that's the only difference, just the same circuit, but these are now going to be positive edge triggered T flip-flops. So we come down and we're going to use, I have set up the transition table for you that you would have in that case, and I have filled in some of the transition table for you to help you make sure that you understand the concept. I've filled in the next value of A and next value of B here, here, and here in these three cases. And what I want you to do, the questions are, what is alpha and what is beta? And then we'll have another question in class. And as this says, for all the questions, assume that we have the same circuit as above, meaning at the top, the one that we looked at in class, the same circuit as above, except that the two positive edge triggered D flip-flops are replaced by two positive edge triggered T flip-flops. So what you need to do is to just go back up here to the circuit, work with the assumption that these are T flip-flops rather than D flip-flops, but that everything else is the same, and then see what differences you would have here in your excitation and output equations, and what difference would that make, what differences would that make in the excitation table, and then what would that give you for the transition table. And again, here's the transition table that you'll be working with, and I have filled in some of the entries for you, and you need to fill in. I've filled in these three, and I've also filled in all the ones for Z, and you need to figure out what alpha is and what beta is, and then in class you'll figure out one more thing. So that's it for this lecture, and good luck.